Okay, so this video is for those like who are just getting into the group theory, trying to figure out what things are. So, what is a group? Let's begin. A group is basically a set, right? A group is a set with an operation defined on it. With an operation. Why am I writing it? With an operation, okay? Yeah, so let's take G as a group, which is actually a set of, let's say, A, B, and C. Yeah, so this is a set, right? Now we define an operation, say star, can be addition, multiplication, anything, not just addition or multiplication, composition of functions, right? What else? I mean, like integer modulo, if you have learned that yet. Okay, so any function, a combination of functions, anything, right? So, yeah, like it can be like a plus b times c minus d, something like that. Anything, okay? So, a set and then an operation for the elements of the set, right? Let me take a concrete example, say Z3. So this contains 0, 1 and 2, right? So the operation for Z3 is addition, modulo 3. Okay, addition modulo 3, and maybe you are not aware of the modulo. So let's take the set of integers 0, then plus minus 1, plus minus 2, and so on. And the operation I'm defining on it is addition, right? This is how we write it. So that means that 1 belongs to this group and say 4 belongs to this group, right? Say negative 4. So our function is addition. That means 1 star negative 4 will be 1 plus negative 4 will be 1 minus 4, which is negative 3, right? So what happened? Two elements from the group operated on each other, and the operation is whatever is defined, right? Okay, so this was a very specific example. Now my focus is actually on the order of elements. So let's get back to the group, our abstract group ABC, right? Now, okay, yeah, a set with an operation, my bad, it has to satisfy the 4 properties, right? It has to satisfy associativity. I'm not writing that. Associativity, then every element should have an inverse, and then there should be an identity element, right? And these are the 3. The first one is that operation. An operation on a set satisfying associativity for every element in that set. Then every element having an inverse and the group having an identity, right? I'm assuming you're familiar with these. I tend to learn things and then I feel they are too simple for me to make a video on them. So I'm hoping you already know this. But if at any point any of the viewers feel that uh, they need a video on something which is like confusing them, just let me know in the comments and I'll do my best to make a video on it, okay? That is the whole purpose of this channel. You're confused somewhere, and like I love to study maths, so I'll try my best to remove that confusion. Getting back to the video, operation, associativity among the elements, all the elements, inverse for all the elements, and identity for the group. Okay, so let's make the C as the identity element, E. Okay, now E is the identity. What does that mean? That means that any element, we usually write small g belonging to the capital G. That means any element belonging to the group. Any element when operated with identity will give us the element itself. Okay, and like we've studied in matrices that if there are two matrices, then AB is not necessarily equal to BA. It is not necessary. That means this property is called commutativity, and if a group exhibits this property for all the elements, it is called Abelian group. The mathematician Abel. Okay, so a commutative group is called an Abelian group. Commutative means every element should commute with every other element. Okay, but even if say this group is not abelian, this identity element, it will always commute. So we can always say that GE equals to EG equals to G, where G is any element of the group. In this specific case, AE will be equal to EA will be equal to A itself, right? Okay, and see if the operation is addition, then this identity element, then AE means A plus E. Okay, and our identity in that case is 0, because we add anything to 0, we will get the same thing back. That is the whole idea of the identity element, right? In multiplication, AE will mean A times E. So we need A back, then E has to be 1 when the operation is multiplication, right? So, yeah, I got distracted by this noise. Anyway, and what about this is identity, and what about the inverse? Inverse is, see, A, then operated with B should give us identity. This is the idea of inverse. This implies that B is A inverse, and this also implies that B inverse is A, which leads us to the conclusion that AB equals BA equals E. In the case when B is the inverse of A, which automatically makes A as the inverse of B, right? I'm talking about this specific group now that we are taking, right? So even if a group is not abelian, identity will commute with every element, and the inverse of an element will commute with the inverse of that element, right? Okay, now getting to the point of this video, which I wanted to like really emphasize on, that is that we often come across the statement that the elements, okay, let's get to the order and then we'll get to this, that why the elements with order 2 are odd in numbers, or they are exactly half, right? Elements of order 2 are odd in number or half. Okay, let's understand this. Before that, let's understand what order is. Okay, my group is my group was this E, A, B. Let's take C and D also this time, right? E is the identity element, standard notation, E or I, right? So what's the order of an element? See, now this is a finite group having 5 elements. Groups, like earlier we discussed the set of integers, which was a group under the operation addition. It was an infinite group. Okay. Now this, what we have is a finite group. And it has to satisfy closure. Did I miss that? Yeah. The first property, what shall I do? Okay. My bad, I will write it in the description. The first property is closure. Like if star is the operation, then A star D will belong to the group, B star C will belong to the group. Basically, for all G1, G2 belonging to the group, G1 star G2 should belong to the group. This is the closure property. If we take any elements from the group and we apply the given operation on them, the resultant will again be an element of the group. It cannot go outside the group. So this thing, the combination of these elements will give us, like, say if A star D is B, okay, and say B star C is A, just random, right? Is it possible? Okay, we'll not go into that if it is possible or not. Just focus on the concept of closure. If we operate 2 elements on each other, we will get another element from the group itself. We cannot get F, which is not even present in the group, right? This is closure. Now, this is an extremely important property to determine the order and to determine this elements of order 2 and this thing specifically, okay? So E, A, B, C, D, this is our group, right? Now, order, yeah, I was telling about the order of the group. Okay, order is nothing like, see, if we take an element A and we operate it with itself, what will happen? We will get A square. Also, if the operation is addition, then A star A means A plus A, which means 2A and not A square. Okay, this elements are just written as A square, like this operation, irrespective of what the operation is, the resultant is written as A square, but it does not mean 2 as the exponent of A. Okay, be careful about this. Now Coming back to the point, order is, see, what if a square is some another element, then a cube not equal to a cube is another element, and then maybe a4 is the identity element, right? What does this mean? This means that 4 is the order of A. A operated 4 times gives us the identity, which makes the order of A as 4. Also, an important thing to note here, if A4 is E, that means A8 will be E, A12 will be E. Basically, A4 to the power anything will be E. Okay? So if you see somewhere that A12 is A12 is E, you cannot conclude that order of A is 12. Order of A can be 1 because it can be something like this. Order of A can be 2 because it can be something like this. Like maybe A square is E and this represents A square to the power 6, right? Similarly, A like order of A can be 3, maybe A cube is E. Okay, so any divisor of 12 can be the possible order of A, right? Now that order is out of the way, how long has this video been? Anyway, I don't care. Let's G E A B, right? Now, yeah, let's understand the elements of order 2 and why they cannot exist in pairs. In pairs as in why there can't be 2, 4, 6. Why there can't be even number of elements with order 2. Let's understand that. Okay. Now what is the order of E? That is 1. Okay. Identity is identity. You do not need to operate it twice to get identity. It itself is identity, right? So order of E is 1. Which brings us to the fact that, let's say, we just have this is our group, let's say. Okay, so, and let's say order of A represented like this, or order of A represented like this is 2. This means that A square is identity. Okay, fine, we are not violating the law closure property of the group. A square is not some other element which is not present in the group. A square is E and that is present in the group, right? So we are just focusing, whatever elements we are taking are of order 2 for now, okay? So yeah, this is a valid group. Now let's say I put another element B of order 2 and I call it a group, okay? Now see, order of A is 2, also order of B is 2. That means A square is E and this means B square is E. But what is A star B? Any element of a group like can combine with any other element. Actually, any element of a group can should combine with all the elements of the group and should result in another element belonging to the group. Now A star B gives us AB. Where is AB in this group? I don't see an AB. Okay, maybe AB is E. Okay, what does that mean? That means that A inverse is B. But you know what I missed? What does this mean? A square equal to E. This actually means A times A is E, and this actually means A inverse is A itself. That means A is self-invertible. Any order, sorry, any element of order 2 is self-invertible. It is its own inverse. Okay, that is how, like, we have the inverse of A in the group. Like, that is a prerequisite for a set to be a group. All the elements need to have their inverse. So E is its own inverse, A is its own inverse, right? But here, if we are saying that AB, okay, like we operated A on B and we did not see AB here. So we said, okay, AB is identity, but that means A inverse is B. But then again, we know that A square is also E. That means A inverse is A, and inverses are unique. No two elements can have the same inverse. Okay, so this means that A is equal to B. That means B is not a different element. B is A itself. And in case B is a different element, then we need to stick in another element AB to this group, to this set actually, to make it a group, to call it a group. We need to have AB there as well. So our group now becomes E, like if A and B are distinct, then they operated on each other will also belong to the group. Okay? And this is why there cannot be two elements of order 2. Because if two elements of order 2 are present, that means they both are their own inverse. But then what is their combination? Where is that element? So it has to exist, right? And this AB is that element. Now, what will be the order of AB? Well, do we see another element? No. So order of AB is again 2. It is self-invertible. This is also self-invertible. Okay. Order of AB equal to 2 means actually AB square is identity. And AB square is not A square B square. No. AB square is AB times AB. Right? And unless we are told that a group is commutative, meaning it is abelian, unless we are like, wait a minute, yeah, unless we are given that, we cannot switch the positions of elements. Like we cannot write A, B, B. We can only write this when we know that BA is equal to AB. That is, when they have said that the group is commutative or abelian, means the same thing, right? So this is why elements of order 2 are odd in numbers. Okay. Now, another thing I said was that if they are not odd, then they are exactly half. What does that mean? It means that, say, E is there, A, B, and let's say order of AB is not 2. That means AB square is another element, and order of AB is not 2, and AB square is another element in the group. Okay. And what does this bring us to? Let me ponder over it a bit. A is self-invertible, B is self-invertible, and we are saying that AB is not self-invertible. that means AB square is a distinct group, is a distinct element of this group. And if we close the group just now, that means that AB and AB square are inverse of each other. This means that AB cube will be E. If I close the set here and I call it a group, then this should imply. Okay. Okay. So yeah, actually, okay, I was confused, but then I recalled that I'm making this group with 5 elements, and 5 is a prime number, and any group which has number of elements equivalent to a prime number, or technically speaking, a group with order 5. Order means number of elements in that group. So a group with order equivalent to any prime is a cyclic group. Okay, so this is isomorphic to Z5. Okay. Okay, yeah. So if it is isomorphic to Z5, I wonder if you are aware of this or not. Order of 0 is 1, order of 1 is 5, order of 2 is 5, order of 3 is 5, order of 4 is 5. Okay, so see, there is no element of order 2. So this group technically cannot exist. Okay, what does that mean now? That means AB square and AB cube is yet another element. Let me get rid of this. AB cube is yet another element. Okay. See, I was trying to stick. Okay, you know what? AB cube. I was trying to fit in 2 elements of order 2, but I mentioned that elements of order 2 have to be half or odd in number, right? So this will be the group. And since it is not cyclic, let's make it isomorphic to S3. S3 has E. Okay, I'll just write A, B, C, then D, E. Order or maybe D3. Wait, instead of S, I'll take D3. Yeah, why not? D3, E, R, R square, R cube is E, then S, SR, SR square. D3 is the symmetry dihedral group of a triangle. So order of these 3 is 2, and of this, order of E is 1, order of R is 3, and order of R square is what? 3, I guess. Yeah, 3, right? So this is how, or this hypothetical group will look like. It will have 3 elements of order 2. Okay. So which is exactly half, right? Okay, you have to practice a lot to understand this, but I hope I gave a fair idea. Okay, so what I was trying to imply is that a group has an identity, then it has elements, and elements combine with other elements, all of them combine with each other, and they make another elements which are itself already present in the group. Also, an element has an inverse which can be itself. If it is itself, then A square is E, and say B inverse is C. That means B and C will combine to give identity and not a new element. However, A and B will combine to give a new element, which let's say is equal to D, right? So this is what happens in a group. Elements either combine with each other to give other elements of the group, or they combine with each other to give identity. In that case, we call them the inverse of each other, or they combine with themselves to give the identity. That means their order is 2. Right? I think enough for this. If you want to understand anything more, just write in the comments, okay?